Okay, welcome back, Math 10s. We're going to do 4.6 here, intercepts of linear relations. It's going to be really similar to our last lesson. And remember, we were graphing lines by creating a table of values. But we're going to create a really specific, simple or more simple table of values where we're just going to be substituting a couple zeros in. We did 0 here for x, and we're also going to do it for y now. And those are going to give us our horizontal and vertical intercepts. So let's talk about what those are first. So horizontal means across. So this means where our graph crosses the x-axis. Okay, where does it cross the x-axis? And then our vertical intercept is going to be where our graph crosses the y-axis. So visually, if I had a quick graph here, okay, we could see, let's escape that. We could see that I could easily graph a line if I know say this is x and this is y, of course. If the x-intercept's right here and say my y-intercept is down here, if I know those 2 points, I have enough information to graph the line. Okay, so let's give that a shot down here. But first, we'll talk a little bit more about how we do that. So to determine the horizontal intercept of a function, okay, again, we could call this right here, also called the x-intercept. We substitute y equals 0, okay? Y must equal 0 when we cross the x-axis. If you look at that visually on a graph here, no matter where I go on the x-axis, y is equal to 0. And likewise, to determine the vertical intercept, okay, so vertical intercept is going to be my y-intercept. We substitute x equals 0 for the exact same reason. Anywhere I go on my x or on my y-axis, the x value is going to be 0. Okay, and to do those, each time we have to solve for the other variable. When we enter y equals 0, we solve for x. When x equals 0, we solve for y. So let's take a look at how we do this. In a little bit of a shorter notation sometimes that I'll be using is x-intercept, y-int, x-int or y-int, but horizontal and vertical intercepts, a lot of times we might just say hi or vi for short. Okay, for our horizontal and vertical intercepts. But in this case, remember that is our x int, and that's also our y int. Just different notations to show the same thing. Okay, so first we're going to be finding our horizontal intercept here. And so that means I have to substitute y equals 0. So we do that in our equation here. We put in a 0 for y is equal to negative 2x plus 5. And now we just solve for x. So we're going to subtract 5 on both sides. That's going to cancel my 5s. I'm left with negative 5 is equal to negative 2x. I'm going to divide both sides by negative 2. And that's going to tell me that my x value is positive 5 over 2, which is also the same as 2.5. So let's plot this point. This then tells me that I can conclude using this and this that I have a coordinate at 2.5 for x and 0 for y. So that's going to be right about here on my graph. Next, we're going to plot the vertical. So we'll call this maybe I'll put it right here, the VI, which again says I have to substitute x equals 0. So we're going to do that now. I'm just going to underline both these to kind of show where both of our work was. Okay, so we're going to be substituting x equals 0. So I take my function up above, y is equal to negative 2x plus 5. I'm going to substitute a 0 in for x. And this one's much easier. Y is already isolated by itself. Negative 2 times 0 is 0. So we get 5. So therefore, we have a point at 0, 5 for our vertical intercept. We have our 2 points, and we can conclude by drawing our, let's go to green. We can draw a straight line as best I can. This is very hard on this pad. There we go. you can definitely do a better job on your paper. All right. Let's take a look at this. We want to find the horizontal and vertical intercepts as well as the rate of change in this graph right here. Well, let's first find our horizontal intercept. Okay, we can just read that right off the graph. If I'm looking at my horizontal axis, this is at t equals 12. Okay, or in other words, if I was graphing it as a coordinate, we would say 12, 0. And then my vertical intercept, we'll get that right off the graph here. This is distance on here. So that's going to be, these are growing up by 2's. So that's going to be at d equals 6. Or if I were to graph it as a coordinate, that would be at 0, 6. And now we can get an easy rate of change here. We can set up our table again. We always put our x value or our independent, right? Our variable that's going horizontal, and we can set up that table with the dependent variable, which is distance in this case. And let's put in these 2 points. So we're going to have a 0, 6. So at time 0, we have a distance of 6. And then at time 12, we have a distance of 0. And this here we can see very easily. We have a plus 12. And here we have a negative 6. Okay, so that easily tells us our rate of change. That's all the information we need for this linear graph. So this is going to be the change in distance divided by the change in time, which is equal to negative 6 divided by 12, which we're going to simplify that down to negative 0.5, and this is in what is our units? Kilometers per minute. So this is kilometers per 1 minute. Again, you could write this as negative 0.5 kilometers per minute. Okay. And so it looks like we have an object, and it's decreasing its speed by 0.5 kilometers per minute. Okay, flip it over and let's look at example 3 here. So first, get a little bit of context here. We have fuel consumption of a scooter with a full tank of gas at the beginning of the journey. So full tank looks to be at a volume of 8 liters and looks to be driving at a constant rate. And this is a function of volume, okay, being as a function of distance. Okay, so distance is our input. Okay, so this is our independent and this is our dependent. So you get a bit of context of what's going on here. The fuel is decreasing the total fuel as you travel further, which makes sense. Looks like this would be where you run out of gas. So we're going to first determine the horizontal and vertical intercepts and describe what they mean. So the horizontal intercept in this case is at, looks like a distance equal to 200 kilometers. And if we were going to describe what this means, I would simply say that this is the scooter's ran out of gas. Scooter ran out of gas. Gas after 200 kilometers. And our vertical intercept is what a variable are we using here? We're using V for volume. That makes sense. So the volume is equal to 8 liters, and this is representing scooter has full tank before trip, before going any kilometers. Okay, next one is what is the domain and range of this function? Well, domain and range, remember, are what are the restrictions on the x variable and the y, but in this case, the d, okay, is our independent and our dependent is the volume. So we're going to first get our range here. So it looks like our range falls between 0 and 200. So it goes from here to here. Makes sense that we don't have any negative values included here. So our range is going to be 0 is less than or equal to D is less than or equal to 200 because that's the furthest we can go before running out of gas. So that is first our domain. Our range is very similar. We can have 0 liters. Oh, sorry, it's using V. Let's erase that. It's using V for volume. We can have 0 liters, so volume, and the maximum full tank was 8. So there's our range for the volume. Again, remembering that domain is the input restrictions and range is the output restrictions. And what is the rate of this function? What does it represent? So we can do this with a quick little table. We can see that D and V, independent, dependent. We start with a distance of 0 with 8 liters, and then we can go 200 kilometers and we have 0 volume. So we can see our change here is plus 200 in distance, but we have gone down -8 in liters. So our rate of change is equal to the change in volume divided by the change in distance, which is equal to -8 over 200, which is simply, once you divide that, you'd get negative 0.04 liters per kilometer. And that's it, that's all. So the scooter uses 0.0 liters or 40 milliliters if we converted that per kilometer driven. All right, that concludes the lesson. We'll see you for the final lesson, 4.7, in the next video.